Efficiently simulating quantum circuits on classical computers is a fundamental challenge in quantum computing. This research presents a novel theoretical approach that achieves exponential speedups over existing simulators for a wide class of quantum circuits by leveraging advanced group theory and symmetry considerations. The technique involves mapping quantum circuits to equivalent forms amenable to efficient classical simulation by representing quantum circuits as elements of a finite group under matrix multiplication, identifying the irreducible representations and character functions of this group, decomposing the quantum circuit into a sum of character functions using the decomposition theorem, and analyzing the resulting decomposition to identify optimization opportunities and potential for efficient classical simulation. The mathematical foundations of this approach are established through several fundamental theorems, including a generalized Gottesman-Knill theorem. The character function decomposition theorem is proven, which states that any element of a finite group can be decomposed into a sum of character functions. This theorem is crucial in enabling the efficient classical simulation of quantum circuits. The decomposition formula for quantum operations is derived by applying the group action to an arbitrary vector in the representation space, yielding an expression involving the character functions chi and the dimensions d of the irreducible representations. Utilizing the orthogonality relations for irreducible characters, the expression is simplified to reveal that the quantum operation can be expressed as a linear combination of the irreducible representations, with the character functions acting as coefficients. The necessary and sufficient conditions for the decomposition of a quantum circuit into a sum of character functions are presented, requiring the quantum circuit to be a group element of a finite group under matrix multiplication, the group to have a complete set of irreducible representations over C that satisfy the orthogonality relation, and the quantum circuit to be expressible as a linear combination of the irreducible representations with coefficients given by the character functions. The proof of necessity and sufficiency of these conditions is provided, demonstrating the validity and uniqueness of the decomposition theorem. Here is a combined summary of pages 58. The authors introduce a generalized notion of quantum circuit equivalence based on character decomposition, formalized in Theorem 3, which states that two quantum circuits A and B are equivalent if and only if three conditions are met. These conditions ensure the existence of isometries relating the Hilbert spaces, identical probability distributions of measurement outcomes, and identical expectation values of observables. The proof of Theorem 3 involves showing the necessity and sufficiency of these conditions using the Hahn-Banach theorem and the Riesz representation theorem. The character function decomposition approach is connected to the stabilizer formalism, generalizing it to any finite group G, decomposing elements of G into sums of irreducible representations. This suggests potential for efficient simulation of quantum circuits using character function decomposition. The decomposition theorem generalizes the stabilizer formalism to any finite group, demonstrating the power of character function decomposition in quantum computation. The research then explores the efficiency of classical simulation for quantum circuits, focusing on stabilizer circuits and their generalization to other groups with suitable representation theoretic properties. The generalized Gottesman-Knill theorem is presented, providing conditions for efficient classical simulation of quantum circuits composed of gates from a finite group. The theorem requires efficient computation of irreducible representations, character values, and the number of irreducible representations growing polynomially with the number of qubits. The proof involves decomposing the quantum circuit into a sum of terms, each corresponding to an irreducible representation, and showing that each term can be computed efficiently. This enables the classical simulation of quantum circuits composed of gates from a finite group. The research paper presents a framework for identifying new classes of efficiently simulable quantum circuits based on their group-theoretic properties. The authors introduce the generalized Gottesman-Knill theorem, which characterizes the runtime complexity of classical simulation. They also propose the revised runtime complexity of classical simulation theorem, detailing the complexity for various group structures. The paper discusses the importance of the term KD2, which accounts for both the number of irreducible representations and their maximum size. The authors also describe their Quantum Forge project, which aims to optimize quantum circuit simulation. They report preliminary benchmarking results, demonstrating significant speedups for certain classes of quantum circuits. Figures and graphs are used to illustrate the reduction in gate count and circuit depth, as well as the scaling advantages of the optimized circuit. While acknowledging the current limitations, the authors outline future work, including testing Quantum Forge on a broader range of quantum circuits and evaluating its performance against multiple state-of-the-art simulators. Here is a combined summary of the content from pages 13–16. The character decomposition method is applied to the quantum Fourier transform (QFT) circuits, resulting in optimized circuits with reduced depth and modified gate structures, as shown in Figure 3. The performance analysis in Figure 4 demonstrates the method's efficacy, with the optimized QFT circuit exhibiting improved scaling as the number of qubits increases, while maintaining the original QFT's functionality. The character decomposition method is further applied to Grover's algorithm circuits, with the performance analysis presented in Figure 5. The optimized Grover's search algorithm circuits demonstrate improved scaling as the number of qubits increases, showcasing the method's applicability to this important quantum search algorithm. The measurement outcome histograms for 4-qubit Grover's circuits confirm that the optimization preserves the algorithm's ability to amplify the target state. The approach is also applied to variational quantum eigensolver (VQE) circuits, with Figure 6 illustrating the significant performance improvement achieved by the character decomposition method. The optimized VQE circuits demonstrate better scaling as the number of qubits increases, highlighting the potential of the approach for enhancing the efficiency of quantum classical hybrid algorithms like VQE. The character function decomposition method provides a new approach to quantum circuit optimization, enabling the identification of symmetries and redundancies in quantum circuits through the use of irreducible representations and character functions. This leads to more efficient circuit designs and implementations, potentially reducing gate count and circuit depth. Future research directions include completing the implementation, conducting comprehensive empirical evaluations, and making the tool available to the wider quantum computing community, with potential applications in quantum error correction, fault-tolerant computing, and beyond. The research discusses the implications of character function decomposition for quantum error correction and quantum algorithms. It proposes leveraging group-theoretic structures to design new codes or improve existing ones. For instance, encoding logical qubits in irreducible representations of a finite group, like the quaternion group Q8, can protect against specific errors. The decomposition method involves identifying the finite group G to which a quantum circuit belongs, computing its irreducible representations and character functions, and then applying the decomposition formula. The Quantum Forge implementation includes several passes for circuit-to-group element translation, irreducible representation identification, character function computation, decomposition application, and optimization. Benchmarks were performed on various algorithms, showing speedups in their execution times. Theoretical complexity analysis was also conducted, highlighting the computational cost of each step in the decomposition process. The paper concludes with a discussion on the significance of the proposed approach and the availability of the Quantum Forge compiler, which will be made open source upon completion.